Let me introduce myself. I'm Jerry Lynch. I'm the department chair of the Department of Civil and Environmental Engineering here at the University of Michigan. And I'm really pleased and proud to present this afternoon our distinguished lecture series that is part of a strategic visioning process that we started in 2017. In 2017, our department went through a process trying to explore what would the future of the profession of civil and environmental engineering look like going forth into this 21st century. And by 2019, we completed our strategic vision that included 5 very exciting strategic directions that we feel will define essentially the identity of our profession going forward. And those 5 directions are human habitat experience, adaptation, shaping resource flows, automation, and smart infrastructure financing. And what this vision does with the 5 directions, it really reaffirms our value proposition as a profession to our communities as we work in service to society. So today we're kicking off our Building the Future lecture series, which is part of our strategic visions, with each of these specific lectures highlighting one of the 5 strategic directions. And today we'll be highlighting the human habitat experience. With this lecture series, we're aiming to provide a forum for discussion around these different strategic themes and really to build a broad community that's part of these themes that's going to include not just academics, but researchers, professionals, educators, as well as students. And what we're trying to also do is to break down traditional barriers between the lab or academia in general and the field, looking for ways to accelerate our efforts in each of these strategic directions as we look to have increasing impact on our society in the realm of each of these directions. So before introducing today's lecture, I would like to say thank you to a few individuals that made this event possible. First, I'd like to begin by thanking the entire Strategic Implementation Committee here in the Department of Civil and Environmental Engineering, an effort that's led by my colleague, Professor Sang-Yoon Lee. I'd like to also thank the co-sponsors of the event. Those include the Taubman College of Architecture and Urban Planning here at the University of Michigan, as well as the university's Division of Architecture, Engineering, and Construction. And then finally, I'd like to thank my colleague, Professor Carol Manassa, who's our Associate Professor of Civil and Environmental Engineering, also the John L. Tishman Construction Management Faculty Scholar, who's agreed to essentially lead today's discussion and to facilitate our panel. I'd like to also just say one word about accessibility. We want to make sure our event is accessible to all participants that are interested in attending. So this webinar will have live automated captions and a transcript will be available. So to choose a viewing option, feel free to click live transcript, which is at the bottom of your screen on the control bar, where you can show or hide the subtitles or view the full transcript of the event as it proceeds forward. Okay, so let's turn attention to today's event. Today's event is designed to highlight the first of our strategic directions called the human habitat experience. And what we're trying to do with the strategic direction is really return people and their experiences in our habitats front and center in our efforts as civil and environmental engineers. This can include human-centered design of how we deliver our infrastructure services to society, all the way to tackling complex social justice issues that may be associated with access to healthy environments to live in. To give a brief vignette of our vision in this direction, we're going to just play a 1-minute video that describes what this direction is about. Rebbe?
Civil and environmental engineering historically have had enormous impacts on the way in which people live their lives. We're focused on all human life. It is global, it is wide-reaching, given the broad impact that civil and environmental engineers have around the world. By referring to the habitat experience, the idea is that we are engaged in improving all aspects of the environment in which humans live, work, and play. We have a number of faculty, Nancy Love and Jerry Lynch, where their projects are specifically designed to go out and engage the public at the very start with the solutions that are being proposed and even bringing the public into the data collection process. We have multiple research projects here looking at ways to make sure that specifically the indoor air is maintaining healthy conditions in residential and commercial spaces. Research that I do focuses on making sure that airborne pathogens don't live very long if they're emitted into the air. There's also research being done where we're using wearable devices to better track not only human comfort, but better track human activity, human safety in construction environments. All of these are ways in which we can personalize the experience to maximize comfort and maximize safety. There is so much more expectation from the public, and as engineers, if we aren't responsive to that, then we are not doing our job.
So along those themes, we're honored today to introduce our distinguished lecturer, Professor Carlo Ratti. Professor Ratti is an architect and an engineer by training. He's on the faculty at the Massachusetts Institute of Technology, where he directs the Senseable City Lab in the Urban Technologies and Planning program at MIT. Professor Ratti graduated from the Polytechnic of Turin and the National School of Bridges and Roads in Paris, and then later earned his master's and PhD at the University of Cambridge. He's widely regarded as a leading voice internationally in the debate on new technologies and their impact on urban life and design. And he's co-authored over 500 publications, including a recently published book, The City of Tomorrow, with his colleague Matthew Claudel. Professor Ratti is also a founding partner of the International Design and Innovation Office at Carlo Ratti Associati. So it's with great pleasure that I turn now to Professor Ratti to provide some opening remarks about our strategic theme and then delving into his main talk. Professor Ratti.
Yes, good morning, good afternoon, everybody. It's a great pleasure to be with you today. So I wanted to share some slides. So let me just share my screen. And I'm really, really excited to, be back in the civil and environmental engineering community. I've been in the School of Architecture at MIT for a number of years, but as you mentioned, before moving into architecture and planning, I did a lot of civil and structural engineering. So really, it's like going back home. So I want to tell you a little bit about the work we do, and I know you're looking a lot about the future of the profession and the future in general. And so I want to share with you how the future looked like around 100 years ago. That's 120 years ago, at the turn of the past century. So in 1899, a number of artists in France tried to imagine how the year 2000 would look like. And they thought that basically this would be fashion. They got some things right. They saw mechanization in agriculture, like you see here. They almost foresaw Roomba. This was their thinking about, Roomba, the little robot that cleans, done by my colleague Rod Brooks and his students at MIT. But they also got a few things terribly wrong. They thought we would move in oceans using whale buses, as you see here, that the aviation police would look like this. And the reason for all of this, because some things right and some things wrong, really it's normal. And if you think about Karl Popper, the great Austrian-British philosopher, he said it very nicely. The future is open because it's based on things we don't yet know. Maybe out of today's discussion later, an idea will come out that might change the course of the future, the course of things. And so he says, the future is open. It's not predetermined, and thus cannot be predicted except by accident. And the possibilities that lie in the future are infinite. So they depend on us, they depend on design, really. Design is a way to turn the present into the future. And we're passionate about design of cities. Here you see cities. I put this picture because I wanted to share with you 4 numbers about cities: 2, 50, 75, and 80. Just remember those 4 numbers. Cities are only 2% of the surface of the planet. They're 50% of the population today, a little bit over 50% of the population, 75% of energy consumption, 80% of CO2 emissions. So if you can make our cities a little bit more sustainable, that could be a big deal globally. And today there's an interesting moment for those who are interested in cities, and the reason is what you see here is the convergence of digital and physical. We could say that the internet is becoming Internet of Things. Bits are merging with atoms and are changing the way we can understand, design, and ultimately live in cities. This is what some people call smart cities. We don't like very much a name. We, for instance, our lab at MIT is called Senseable City Lab. We like the idea of technology. We think that smart city sounds a bit like technology for technology's sake. Like city like a computer in open air. We like the idea of sensible city, a city that's able to sense, but also sensible. And so Senseable City Lab is where we do all the research at MIT, where I teach. That's primarily in Cambridge, Massachusetts. MIT also has a small research lab in Singapore, so we got a Senseable City Lab Singapore. It's with our design office in New York, in Italy, in the UK, and with some of the startup that have been coming out of both the office and the lab. So I wanted to start by showing you some projects, starting with research. If you look at this, that's a city like you couldn't see a few years ago. It's a city like a living organism. It's actually the city of Lisbon in Portugal, mapped using billions of data points collected from the mobility network of the city. That's actually a visualization that was done by Pedro Cruz, who was in our lab at MIT, and the visualization was at MoMA, the Museum of Modern Art in New York. But again, it shows you a city like we couldn't see just a few years ago, but we can today. And then if you take the data behind that visualization, say similar data, that's what you see here. This is actually taxis in New York. What you see here, every dot is a taxi pickup or drop off. A yellow dot is a pickup, a blue dot is a drop off. What you see here is actually JFK Airport. If you zoom out, you see JFK Airport was in the lower right corner of the city. And then you see Manhattan and all of the boroughs. And then if you get all this data, you can ask yourself different questions. The first question we asked a few years ago was the following. If you look at those 2 points, there's hundreds of thousands of trips, taxi trips, connecting them in the course of the year. So how many taxi trips could be shared? And the idea and inspiration for this project was what I experienced many times in New York and other cities, but I think many of you as well. You're out of your hotel, you're going to the airport, you're waiting for a taxi, and there's somebody else next to you, also with a trolley, going to the same airport. But you're taking 2 different taxis while you could have combined those trips and saved a lot of energy, congestion, and so on. So we wanted to quantify that. Now, when you get all this kind of data, big data, and you want to analyze it, well, sometimes we say big data requires big math or new math. So we developed a new mathematical approach. We call this Shareability Network. So we use network science to answer the question I said before. Mathematically, you phrase it this way. Imagine you want to take everybody to destination when they need to be there, give or take 1, 2, or 3 minutes, a small delta, that's your parameter. Then what is the minimum number of taxis you need? And again, going back to my previous point, the standard way to answer that question traditionally would have been linear programming, but linear programming doesn't work when you got so much data like in this case, so you need to find a new creative way to tackle the problem mathematically. Here you see this kind of shareability networks. Again, if you're interested, I'm putting screenshots of the papers. You find all of them on our website. So, and you can download them freely. So if you're interested, you can just look at them in more detail. And what we discovered is quite interesting. In New York, you could take everybody to destination when they need to be there with a small delta. You see it here in the upper right side, in the upper left graph. With a small delay, 100 to 100 seconds, but with 40% less taxis, less vehicles than what you have today. Now, an interesting story that actually when we did this paper, Uber Pool didn't exist yet. And actually, Following the paper, we started a collaboration with Uber, the first collaboration between MIT and Uber. And as you might know today, Uber Pool does exactly this. Uber Pool and many other services like Via now, and many others have come up. Didi is offering the same, Grab in Asia, Ola, and so on. So are offering this, which is sharing 2 trips. And when you're sharing 2 trips, again, you combine 2 trips into 1, which means 1 less car on the road, which means less congestion, less consumption, and less pollution, potentially, all other things being equal, less pollution in our cities. Now, that's a more recent paper where we looked at another question using the same data set. And here we ask ourselves another question. So before was about car sharing, ride sharing, sharing the ride. Here is about how we do better dispatching. And so we called it the minimum fleet problem. What is the minimum number of vehicles we would need in New York, no sharing at all, but just optimizing dispatching? What is the minimum number of vehicles we need to, again, satisfy all the trips we can measure today from the same data set? But again, just by optimizing the dispatching. I mean, what is the inefficiency of the system today that lies in the dispatching? And that is the results are quite interesting. I think we didn't, when I connected, we didn't share sound. So I'll share again the screen sharing sound. So hopefully you can see you can hear the sound with the video that I'm showing you next. So I hope you can both hear the sound and hear me. Yes. So, so what you see here is again the taxi data in Manhattan. You see them here. It's real data, again, collected from the Taxi Limousine Commission. And they're vacant half of the time. They're looking for passengers. Dispatching is not very efficient. And so again, we applied a similar network science approach to solve this minimum fleet problem. What is the minimum number of vehicles we need? And what you see here to the left and to the right in a moment, here you see just a visualization of the algorithm, but to the left and to the right, you see to the right the present day condition. And to the left, we're not changing anything, not asking anybody to share, not changing anything, but you could cut a lot of vehicles just by optimizing dispatching. This could be done tomorrow in New York, everything else being equal. And if you look at that, if you're looking at the text, if you look at the future when we got self-driving cars, then potentially we could actually keep Manhattan on the move with 50% of the vehicles we have today, all things again being equal. Again, if you're interested in this kind of minimum fleet problem, this is the paper that was a couple of years ago in Nature. Actually, we have a good follow-up paper in Nature that's coming out in the next few weeks that actually builds it on this, but I'm not allowed to talk about it until when it's published. Now, so far, I show you what we can do when we look at the vehicle as a probe, basically with the position and the time. So you got lat, long, and time, and you analyze it. You can do the type of analysis we saw before. But the vehicle itself is becoming like, a bunch of sensors on wheels. And you see it here, that's a project we're doing with a large car manufacturer. And, that's the data collected by the car is usually 2,000 or 3,000 signals collected in real time. They collect everything, temperature outside, inside. Do you have your hands on the steering wheel? How many people are in the car? You got sensors that detect occupancy of the seats, and so on and so forth. So basically, you got this kind of 2,000 or 3,000 signals. And so you can start to use the car as an ambient sensing platform. If you look at this paper, by the way, you can see many applications, also environmental engineering applications. You can use the car in order to micro meteorological models because you know where it's raining exactly. So in the future, where every car is connected, you got this kind of huge amount of sensors that can collect information about our cities and the environment. But thinking about more about structural engineering, you can also look at data collected by the car to look at the stability, at the structural health of bridges. Now, let me tell you a bit more about this. So, some of you might have seen this. This was a collapse of a bridge in Southern Europe a couple of years ago. But there's many other bridge collapses. They're very familiar to structural engineers. This is a very well-known and documented Tacoma Bridge failure in the United States. Or I'll tell you a little story about this bridge that's called Longfellow Bridge. It's close to MIT. The MIT campus is to the left. Boston downtown is to the right. Well, Longfellow Bridge was being used by everybody. I would cross it almost every day until a few years ago when, they did a few structural tests on the bridge, and they realized the bridge was close to structural collapse. So the bridge had to be stopped. The two sides of the city were cut. The bridge was cut off, and the two sides were not connected for a number of years. And it had to be rebuilt at a huge cost to the community, to the government, of several $100 million. And the reason for that is that the bridge wasn't being monitored. Today, if you want to monitor a bridge, you either put sensors, as you see to the left here, or you send people. But monitoring a bridge this way, putting sensors, cables, collecting the data, sending the data to the cloud, analyzing the data, sending people to do inspections, that can set you off up to $500,000 a year per bridge. So we couldn't do this in all the bridges in the United States. So our point was, the data we collect when we put sensors usually is this kind of structural fingerprint based on the vibration frequencies of the bridge. And so we started saying, well, our cars actually collect a lot of data about vibration. They got accelerometers and gyroscopes, and also our phones collect this type of data. And what you see there, otherwise in orange, is a professional accelerometer. So we said, what if you could actually use this information collected from large fleets in order to understand the structural health of bridges? And we decided to start our analysis on this bridge. Why the Golden Gate? Well, because the Golden Gate has been studied so extensively that we got a perfect ground truth. We know everything about this. So this was our starting point. So we started going back and forth across the bridge with the car, collecting data, the car, a few phones, and the accelerometers to collect different signals. We went back and forth over 100 times. Then the San Francisco police got a little bit suspicious, so they stopped us, and we were not allowed to cross the bridge anymore. But we collected enough data. That's the raw data that we collected, you see here. And then when we analyzed it, we realized that actually the key frequencies of vibration of the bridge were there. And since then, we've got another paper coming out soon that's under revision, is undergoing revisions, where we started looking at data from fleets, especially fleets from Uber again. We're also working with a fleet of 100,000 cars in a big European country, in collaboration with Allianz, the German insurance company. And so using a lot of this data with fleets, trying to really expand this and do in one go, just with an app, try to understand the structural health of all the bridges in a country with a very, very small price tag. This is data that comes almost for free. I say almost because yes, there's a bit of cost because of collecting the data, transmitting the data, whatever 5G transmission, but it's really inexpensive. Again, we are still working the results. We got this paper coming out. We're still working the results from the large fleet. It's not as precise, of course, what you can get if you put real sensors on each bridge. It's a bit like when you go to hospital. They first measure your temperature and your blood pressure, and then, if needed, they send you to do whatever, an MRI or more precise analysis. So in a similar way, we can start doing this with our bridges. And, we're telling you this comes from all the sensors we got on a vehicle, but we can also add additional sensors. So what we did in this project, in Cambridge, we started using garbage trucks in order to add a platform for sensing the city. So what we discovered when we turned garbage trucks in a platform for sensing, and we created this kind of modular platform with a bunch of sensors. You can also change them over time. And then, temperature and humidity, of course, air quality, infrared, and so on. And the interesting thing is that basically garbage trucks go everywhere, in every street, at least once or twice a week, even more. And then we collected all the data. We started sharing it with people in Cambridge, which is interesting. Again, what you mentioned before in your video that I thought was very interesting, how you can engage people and citizens. And here, a lot of people started, looking at the neighborhood and writing to the mayor and say, what is the problem here? We need to fix it. We need to address air quality or whatever. And actually, so we are scaling this up. Now we are scanning New York City, and we are expanding this in many cities around the world. But again, as a way to create a small platform to collect data. And I want to share with you also something interesting. You can put this on garbage trucks. The interesting thing about garbage trucks is that they go everywhere in a very systematic way. So you need to get trash from all of the bins, from every home, and so they need to go everywhere. But then we ask ourselves, what if we were to put sensors, say, on taxis or on just random vehicles? And here, actually, you see collecting data from vehicles don't remember this one. It's not Singapore. It's one of our cities. I've forgotten which one. I forgot which one this is. And the interesting thing is that when you do that, we discover some interesting mathematical regularities. This is what we call the sensing power of vehicle fleets. And we started looking at real data from fleets of vehicles in different countries, and we saw that they follow a very interesting curve that you can predict mathematically. So we developed a small mathematical model that actually gives you a very, very good prediction. You see it here. The red are the experimental data points. The two curves is what you predict with the model under two different conditions. And but it's really a very, very good match. And the interesting thing is you see the curve is very, very steep at the beginning. Is a little bit, it follows like, the upper part of a sigmoid curve. So, it grows very fast. And so what you're seeing, if you look at 0.5, to scan 50% of the street segments in the city, you need such a tiny fraction of vehicles. A few dozen of vehicles in New York City will help you to scan, in this case, once a day, almost 50% of all the road segments in the city, which again is very interesting. And if you can predict it, you can see what's the best way to deploy your sensors on a mobile fleet. And of course, if you got a mobile fleet, that leads to another question, which is, traditionally sensors were static. So sensors were static, and we'd also consider population as static. Now, as we just saw, we can put sensors, moving sensors, so we get a better understanding, dynamic understanding of the city. But also we need to realize that the populations are also moving. The problem, if you are a mayor, is not necessarily to minimize air pollution across the whole city. But if you've got limited resources, you want to minimize air pollution or improve air quality in the places where you have more people. And as you know, population change is dynamic during the course of the day. We move from residential areas to offices. So, and here what we started doing, we started looking at cell phone data and also very fine-grained pollution data in order really to see how we can change our thinking, which is going from just, improving air quality in a uniform way to improving air quality when it can have the largest effect on people. Again, if you've got limited resources, you can try to maximize your results, which is minimizing exposure. So we call it exposure track. Again, you see here, so the impact of mobile device-based mobility patterns on quantifying population exposure to air pollution. And we're working still a lot on this topic. Now, I wanted to add you something else. So we looked at mobility and we looked at sensors, and if you add additional sensors to your car, such as those two little ears that you see those are LiDAR sensors. They collect 3D information about the city, like you see here. You feed it into an artificial intelligence system, and you got a self-driving car. Now, we are not at level 5 yet, but still we have thousands of self-driving cars being tested as we speak around the world. We've been very involved with the Singapore government's effort in order to develop self-driving cars. And self-driving cars are going to change a bunch of things. Today, a car, believe it or not, is used only 5% of the time. 95% of the time, it's parked somewhere. But if you've got a self-driving car, that can change. It doesn't need to be parked all the time. It can keep on giving a lift to somebody else in your family or to anybody else in the city. So, for instance, in some recent work, we've been looking at Singapore. Again, as I said, 95% of the time today, a vehicle is parked, which means in Singapore, we got almost 1.4 million parking spots. That's for a city with around 700,000 vehicles. But if we were to move to a self-driving system where cars keep on moving, then we could cut it down by 70 or 80%. Depends a little bit on your assumptions, and we have them in this kind of two papers. In this first paper and in this recent paper in Nature Scientific Reports, again we call it the minimum parking problem, where we look at this kind of trade-off. Of course, if you go self-driving, you could say the minimum is zero. The cars can keep on running always on the road, but that's probably not desirable because you pollute much more. So again, you get a little trade-off, but we see that we could actually cut up to 80% in this paper with a very small increase in total miles traveled. And another impact of self-driving on the city could be this. We're all familiar with this. It's a well-known traffic light, and traffic lights arrive on our roads when actually cars arrive on our roads. But if you got an intelligent system where the cars know where they are and where everybody else is, you don't need traffic lights anymore. You can keep on going, just avoiding collisions like this. Don't try it yet. I've shown this in the city of Naples in Italy, and they told me, so what is new here? And I'm Italian, so I can make such politically incorrect jokes, but a former Italian minister once said that in Milan, traffic lights are instructions, in Rome, they're suggestions, in Naples, they're Christmas decorations. So anyway, these are some of the work that we're doing. Again, here you can mathematically model the intersection. Look at, we expanded queuing theory here to model the intersection. That's the paper if you're interested about revisiting street intersection, use slot-based systems. I want to share with you a couple of additional things. Just to wrap up, I'd like to have a longer conversation. I've got many more slides, but I think I'd like to finish in a few minutes and then have more discussion. Now, so far I showed you the research. In our design office, we design neighborhoods, buildings, cities, but also more speculative projects. This is what we did for Google, looking at how we can think about the road with self-driving cars that can be reconfigured dynamically. You see the road in the morning can have a lot of lanes for cars. All of them are actually Waymos. So Google's siblings company, Waymo, for self-driving cars, moving there. But in a few hours later, it can be used for kids to play, or in the evening, it can be used for a park, for a party. And so actually, there's a prototype of this that we did for Google that works quite well with a little robot that reconfigures all these different elements. Again, we can reprogram cars. As we saw before with intersection, we can start thinking about the city as something that's much more dynamic. In a similar way, in this project, we won a competition by the city of Paris. The competition was called Réinventer le périphérique, reinventing the peripheric, which is a ring road in Paris, the main ring road. And we looked at things such as, again, can we look at how many lanes we dedicate to one thing or another thing dynamically? If cars are self-driving, getting programmed just digitally, can we look at producing energy? Now, today, you go systems putting photovoltaics on the road, they exist. Unfortunately, they're still a bit more expensive than putting photovoltaics, on flat land. But somehow, if we manage to decrease the price, that this was, by the way, a vision towards 2050. So if we manage to decrease the price of photovoltaics, that could be quite interesting because we got an infrastructure that's basically self-powered. You get all the energy you need and you use it to power mobility over there without having to consume agricultural soil. Or also the fact that with AVs and EVs, so with autonomous vehicles and electric vehicles, we're going to have most likely less pollution, less noise, and more safety next to the big ring road in Paris. So buildings can somehow get back and bridge across the highway. Now, I'm a structural engineer myself, as was mentioned before, so don't ask me how the beautiful span made of glass can function. But that was more our team's 2050 architecture. Our architects in the office did it. I didn't want to disappoint them, saying it wasn't feasible. So thinking about 2050, maybe we can all try in the next 30 years to make that feasible. And then I want to finish with this. I talked a lot about cars. But we're not particularly excited about cars. Personally, I don't own a car. We're excited about cities, passionate about cities. Self-driving can help us, make mobility more efficient. And so I want to tell you a little story. It's a story of the first startup we created at MIT. From MIT, we got now 6 companies, 3 in the United States, 3 in Europe. The first one was called Super Pedestrian. And it started producing this, which is it's called this Copenhagen Wheel. The Copenhagen Wheel is what you see there, the red dot. You put it on a bike, on any bike, and it turns your bike into an e-bike. And we presented this, we call it the Copenhagen Wheel because we presented this with the city of Copenhagen to a big summit with President Obama and others. And then, the wheel went viral, so we got funding from VCs and started the company. Now, this is what we did for the first 3 years. We set up we raised VC funds, and then we started the company, the factory. We started producing this, and then we realized that actually the market wasn't that big. So 3-4 years ago, we didn't know what to do. The market was there, but not for VC standards. VCs are not interested for you to build like a $100 million company, even if that could be a good endeavor and something good for society. They want you to build at least $1 billion company or to capture $1 trillion market. I mean, they want you to think big. So anyway, we didn't know what to do with this, but at the time was the beginning actually of micromobility. Micromobility is all the scooters, the dockless bikes, and so on that you find in all of our cities. And while doing the wheel, the Copenhagen Wheel, we actually filed a lot of patents in order to do remote diagnostics and also remote maintenance. So again, we put thousands of sensors, well, in that case, probably not thousands, but we put hundreds of sensors into the wheel, collecting all the information about the wheel and allowing us, because we engineer everything from scratch, allowing us to really understand much better what was going on and also fix many problems, both with hardware and software. So we had filed many patents, so we gave it a try and said, what, maybe we're going to be competitive in the micromobility space. And so we started moving from the Copenhagen Wheel into fleets and fleet of scooters. This was actually just a few weeks ago. So we got a last round of around $60 million for a push in New York for this. But we actually already in many cities every week we're opening new cities around the world. And it looks like this was the Italian one. I was particularly proud when, as an Italian, when we got awarded Rome. And now I think a few other cities, Turin, I think is coming in a few weeks, and so on. But the interesting thing was a nice story. 2 little things. The first one is, if you do a startup, like more and more of our students are doing, and I'm sure also a lot of you here listening. First of all, never, don't be concerned. You got ups and downs; they're normal. And never mark to market. Never think about all of this is one day you feel you got something that's worth a lot. The other day you're bankrupt, and that's really normal. So you need to take it more like something fun here, something not only fun, but that can help our cities. So the reason I'm excited about this, and I hope, I think at the moment the company is doing amazing. Maybe it will have issues again in the future. But I think what I'm excited about is that micromobility, I believe, is going to be very good for our cities. Remember where we started when we talked about, cities consume 75% of energy consumption globally, 80% of CO2 emissions. Certainly, it doesn't make any sense to move an SUV, 1 or 2 tons of steel for normally 1 or 2 miles in a city, just to move around, to shuttle around 150 pounds. So that doesn't make any sense. And micromobility is interesting also because it makes mass transit much more efficient. So you can get off the subway, you can get off the bus, and then you take a scooter or you take a bike and you do the last mile, and the 2 complement each other. So again, the micromobility was not working until a year and a half ago. Lime was going bankrupt at the beginning of this year and got a down round by 80%. So if with artificial intelligence and sensors, we are able to change this industry, it's not only about super pedestrian links, it's our brand of scooters, but we can, make mobility more sustainable in our cities. So I wanted to finish here. I didn't show too much about startup and design. I just showed two examples here at the end. I focus mostly on research, but I'd love to hear more from you and have a conversation. And if you don't have questions, I will restart with my slides and flood you with another 300 slides before the end of the hour.
Thank you very much, Carlo. This was really interesting and very informative and thought-provoking conversation. And I hope we can continue this in the panel discussion right now. For those of you who joined us late, my name is Carol Manassa. I'm an associate professor in civil environmental engineering at University of Michigan. And I will be moderating the panel discussion to continue our conversation. Before we start, I would like to welcome our three panelists to the discussion. Of course, Professor Carlo Ratti from MIT will be one of our panelists. Professor Kenichi Soga, who is the Donald McLaughlin Professor of Mineral Engineering in Civil Environmental Engineering at University of California, Berkeley. He is also a faculty scientist at Lawrence Berkeley National Laboratory. Professor Soga's research interests and activities are in sensing and performance-based design of infrastructure systems. Also, I would like to welcome Professor Jeffrey Thune, who is a professor of architecture and a senior associate dean for research and creative practice at the Tubman College of Engineering here at University of Michigan. Professor Thune basically supports Tubman College's research enterprise and seeks to enhance and strengthen the vitality of research across the architecture, urban, and regional planning programs. Join me in welcoming our three panelists to this session. I know due to technical difficulties, we are running a little bit late on the program, so I hope you'll be able to stay a few minutes after 2:30 with us as we continue this very interesting discussion. So the questions that I'm going to start the conversation with are actually questions that have been curated from a list of questions submitted by the audience who has registered for the seminar. So let me start with the first question. So what do you think are the main justice, equity, and fairness challenges associated with the implementation of these technologies that we just looked at? And then I guess embedded in this question as well is, are there any efforts to ensure that biases, whether racial, gender-based, ability-based, are being eliminated when we are looking at this data and this information? Carlo, maybe we can start with you.
Should I start myself? Sorry, I thought because I spoke already too much. But no, I think that's a great question. I'll be very short. I think the issue of data is a huge issue of data. It was at the center of actually something I curated in China last year, the Shenzhen Biennale, and all the data that's collected and how it's being used is a huge issue. And who controls the data? There's an incredible asymmetry. We got companies and states who know everything about us. We know very little about them. Long story short, I think the important thing is that we are all aware of what's going on and all discuss it and try to take political action. I think we need to move towards a society where there's more asymmetry, there's more transparency, both in who has the data, how data is used, but as you're saying, also in the algorithms. The only way to avoid biases is if also the training sets in the algorithms that are applied to data are open for scrutiny. We can look into them. Otherwise, there's really no way to see for anybody to be able to find those biases that will reinforce, discrimination and anyway, could be super damaging in society from different points of view. So anyway, the thing is about transparency, symmetry, openness of the algorithms and the training sets. I think those are the principles, and that should come from a discussion altogether about such topics. At MIT, twice we did a conference called Engaging Data, and maybe we'll hopefully after the pandemic would resume the conversation. It would be great maybe to do it together. I think it's really an important issue for the future of our society and democracy.
Thank you. Kenichi?
Yes, thank you very much for having me today. As you can see from my background, I have a San Francisco Golden Gate Bridge, which is actually 84 years now. And it's a really aging infrastructure. And what I want to also discuss today, we saw a lot of interesting data sets, but then also we are looking at civil engineering at a much longer term view of our infrastructure. So when we talk about the bias and everything, I also feel that we should look at longer term, because bias will change with time sometimes. And that's a very important thing to recognize, is that how we accommodate and be flexible enough to encounter this bias, and then trying to sort of cope with that and then deal with it. So I think when we discuss about bias, I also think that we should also think about the history of the bias, but also future bias. How do we change and make sure that we cope with that kind of changes in the future? So my theme will be more longer term today.
I mean, I'd love to just reference one of my favorite texts on the moment about this topic, which is Ruha Benjamin's Race After Technology, Abolitionist Tools for the New Jim Code. And what's so fascinating about her work is that she centers the question of discriminatory design, that is, human decisions, assumptions, and values that shape the process of technology development. And by kind of revealing these issues, we're able to see not only underlying flaws within existing systems, but to shape the conversations and orientations about what we privilege moving forward. So I'm fascinated, by the way, Carlo, about the work that you and your lab are doing at MIT. It's fantastic. But it becomes a super interesting question to start thinking about the priorities that aren't necessarily advanced by some of the sponsors that are pushing work forward. My favorite story right now about mobile sensors is thinking about how Ford's privileging the use of sensing on the government fleet to provide real-time visualization of PM concentrations that might be used to predictively determine how you staff ERs. So asthma events, of course, peak in California. This is the primary driver of ER doctor demand in an ER situation. So sometimes thinking outside of the questions of optimization within a kind of constrained question, start to open up, I think, really interesting ways to reorient the use of data that's coming from some of the intended outcomes of technological application. And in the case of Ruha's arguments, I think we're talking about fundamental paradigm shift, how to start about rethinking what's situated at the center of the operation of the algorithm, or what inherent bias even resides within the type of sensor. So if we're thinking about optical sensors, for example, that privilege data essentially coming from light spectra, this immediately maps onto questions of skin tonality. Whereas if we're thinking about an IR sensor, we're thinking about warm bodies. And so the question of skin tonality or race is immediately blind to that sensor. So when we're thinking about applying particular technologies, also the biases that reside in the kind of algorithmic logics of the system control, we can even think about the fundamental physical components of the system as contributing towards a kind of context of bias. So, I mean, I think that's a super interesting issue, particularly within discussions of advanced technology, to be prioritizing not as a secondary or tertiary concern to the discourses, but rather as a primary question about how we think about what constituencies we're serving and what we aim to produce.
Thank you. Thank you very much. So I think we received a very interesting question in the chat window related to the conversation that Carlo has started. So the question is, we have seen that in the US, there is significant focus on improving the technology with cars. So moving from, like, historically, as you have showed us, from what we had earlier with the idea of using whales as buses to shuttle people, all the way to now where we're focused a lot on autonomous vehicles and autonomous mobility. So the question is, what about the urban environment, and what about how we think about our own infrastructure, the bridges, the streets, the roads, and why there isn't that much focus on how we can make shifts in those infrastructure to support better urban mobility, support sustainability environments. So what are your thoughts on that? Carlo, you are muted.
Yeah, sorry, apologies. I think "you're muted" is the most spoken word of the year, and since we went on all on Zoom. So no, I'll try to be super quick. I think it's a very good question. Now, However, keep in mind the following thing. I mean, we just heard about the Golden Gate being 85, more or less 85, 84, I think you said, year-old bridge. And, you know, when we build a new bridge or electricity infrastructure, this is going to last, whatever, we build this certainly for 50, 100, or even 200 years. When you think about technology, you know, it's surprising to think that in the year 2000, people couldn't figure out that we could have self-driving cars. A few colleagues of mine wrote a paper in the early 2000s where they were saying, you know, what are the jobs that will always be safe from automation? And, you know, one of them was truck drivers, because, you know, they couldn't foresee self-driving coming. And so technology is changing much faster, certainly not on the scale of 50 or 100 years. You know, we didn't have Uber just, 15 years ago. So somehow we need to build our infrastructure in a flexible way. And I don't think it's that much about redoing the infrastructure. I think it's about using it better. And somehow I would say that today the most interesting thing is how we can transform our cities with less asphalt, less concrete. You know, concrete is, from a sustainability point of view, it's really not the best thing you can do, also in terms of CO2 emissions and all of that, and circularity. So less concrete and asphalt and more silicon, more intelligence. So I feel, instead of thinking about building more infrastructure, how we can repurpose and reuse better the one we have, especially through intelligence, through data, through sensing, and through systems that allow us to make the most of it.
Yeah, I echo that with that, what Carlos said, is that if you look at the Golden Gate Bridge, for this one, I think it's a very lucky one because people use it all the time. But then at the moment, it's congested. So then, but it's too old to change, to expand or shrink, whatever it wants to do to change, because it was built in a very rigid way. So having a more flexible design that we don't do is important to think about. And I'm an undergrad, I do a lot of underground construction design and that sort of thing. So we design everything 120 years. And typically when we bury a pipeline, you're not gonna see for another 120 years. And for me, it's a missed opportunity, is that we can put intelligence in a pipeline. There may be a possibility to use these systems. Even though you don't see it, we know what's going on. And I think that's where the adaptation and flexibility of our design should change, rather than trying to say, okay, it's 120 years design life. Because as Carlos says, city changes so rapidly. The industry we have right now may be different in 20 years' time. And we also see in other cities, they have big industry, but then it declined because it doesn't have that industry anymore. So the change in industry is going fast. The society is changing rapidly than the 100 years of our bridge or something like that. So at the moment, if we can make our infrastructure a little bit more sensing, then allows us to understand what's going on. And then looking at the demand changes, as Carlo nicely presented, then we can see how our Kiwi infrastructure, hard infrastructure, can be adaptive, meaning it can expand to cater the sort of a demand in an elegant way. But if the city is declining, you sort of shrink, but then it shrinks in an elegant way because we know what's going on. So I think sensing in both how people are using the city, but at the same time, if we can have opportunity to embed sensor to our infrastructure so that infrastructure can be adaptive to changes in the way that we see already in the past 10, 20 years, is something that we can think about when we design our infrastructure.
And I completely concur with Carlo's comment on rethinking material streams from extraction to end of life, and rethinking the material compositions and systems with which we construct our environment. Also with Kenichi's comment regarding this question about how we can think through the lens of adaptation to begin to demand that our infrastructures can do more. But central to that discussion is really a fundamental paradigm shift. And I'm making this comment in the context of thinking around the frameworks of logic that drive civil engineering discussions in the last 200 years, which is we have attended to think around systemic performance through singular lenses. And I think the infrastructure of the future need to be conceiving of operating in multiple domains. I really appreciated the image that Carlo showed around just even the simple idea about rescripting the use of public spaces as a format of infrastructure during diurnal or seasonal cycles. That's one way to begin to think about these issues for sure. But when we talk about sustainability, I guess I wonder what we're talking about. Are we talking about the minimization of negative impacts of action? Are we talking about generating resilience, which is a separate issue, which is primarily around responding to specific peak events? Are we talking about achieving systemic circularity? What are we talking about sustaining? Are we talking about sustaining the dominant systems that characterize our urbanism, that is systems of poverty and systematic disparity? You know, like, I think these are kinds of questions that need to be central in the training of the next generation who's going to think around the future of infrastructure, so that, again, it's not an afterthought about a filter, it's core to the rethinking, which right now, right, privileges optimization, regardless of the lens of the question. And I think that's a huge issue we need to center. This idea of multifunctional infrastructure, that which can serve multiple constituencies around multiple agendas, as a new model through which we ask, how can we produce abundance rather than optimize towards minimization of an issue in a framework of scarcity? And I'd just like to just add to the conversation here, this fascinating text that for me is center to many of the ways I try to think about systemic performance in infrastructure, which is Donella Meadows' text from 1999, Places to Intervene in a System, in which she talks about the ways in which one might be able to think about changing the performance of the overall system, which is precisely what each piece of physical infrastructure is aiming to do. It's instrumentally, either as a vector or a node, trying to participate with a networked systemic framework to alter performance. And it's a fascinating text in which she unpacks from the least effective ways to intervene, which tend to do with minor moments of optimization or the adjustments of levers and flows, to ultimately one of paradigm shift as the optimum way, the kind of most remarkable way to constitute change within a system. And so for the young folks who I think are listening to this, maybe, that we don't see you on the screen, that would be something I just want to center for you. How do we think about changing the paradigms in which our infrastructures operate as part of the moment of their conception?
Just a quick thing, by the way, I want to say I'm seeing that in the Q&A from the attendees, there's actually a few nice questions that I think, I don't know if we're missing because we're looking at the chat, which is among ourselves. So do you want to mention that? And maybe just in really less than 30 seconds, I wanted to share with you something just because, you know, again, I didn't show you the work we're doing in our design office, but circularity, I think now is vital, is imperative. You know, you mentioned it a moment ago. And in this project, what we try to do is actually to do a structure. In this case, you know, all these arches are made of mycelium or mushroom, and we basically grew them out of soil, became an architecture, and composted it at the end of, you know, this was for an exhibition, composted it at the end. I want to show you as some of the experiments of how, you know, I think, you know, this is all mycelium, so you can compost it in just a few weeks afterwards. And I think, you know, one day, hopefully, we'll be able to design buildings, you know, with the same intelligence that nature uses, you know, that actually is able to harvest both materials, raw materials and energy locally, create amazing structures as you see there, and then, you know, do all of that in a circular way. So that was just a quick response, again, you know, to sustainability. Of course, then we got social sustainability, but at least for environmental sustainability, I think we should all try to go in this direction.
Thank you. So in the interest of time, I'm going to ask one more question and also ask our panelists to provide their I think their positive thoughts about the future of our cities and our urban environments. Obviously, in this time and age, we cannot avoid the question of COVID and its impact on how we are using our mobility systems and our infrastructure. So the question is related, how has COVID impacted how you imagine the future of the urban built environment?
Who should go first?
It's up to you.
I'm happy to take it. Look, I think first of all, we'll be surprised, I'm pretty sure, to how much we want to go back to our streets. It's no surprise, I believe, that the 1920s were the roaring 20s, were certainly not a time of introspection, were a time of great urban and social excitement. And, I'm pretty sure we'll see a lot of that. I see a lot of pent-up demand for being back together. And you know what? Digital is great. We can also be more sustainable. Teaching has been much more sustainable in conferences over the past 12 months. We should certainly keep some of that. But there's something very dangerous about digital. And what is dangerous about digital is that digital, we know it, it tends to lead to polarization. We end up in echo chambers where we only talk to people who are similar to us. That's what we've seen politically. It's so easy to just exclude all of those who challenge our comfort zone and just end up in this echo chamber that little by little become more and more radicalized. And I think there's one antidote to that, and that is physical space. Physical space, the space of the city, the space of the office, is a space where we are challenged all the time, where we meet people we don't necessarily want to meet. We meet random people who might open our mind with different ideas. Those are not the people we meet on Zoom, on Skype, on that. So I would say post-COVID, I think this is certainly not the end of the city. I think we need cities and public space more than ever, because that's where we come together. That's where we can really make sure that cities perform their primordial function, which is bringing us together so that together we are more than each of us individually. But
yeah.
sorry, I want to say just as this is the last one, I want to say maybe because I saw those kind of the students asking some question, I wanted super quickly maybe just out of courtesy to say something. Somebody was asking about micromobility. What about weather? I think it's a great question. I think we see more and more small solutions, small micro car for one or two people. We're also working on that. It will be micromobility, not just a scooter, but something more like that. The second question was about sharing data. Yes, we share all the data. That's why we do great. We try to do a lot of data visualizations, and in particular the data about pollution we always share with the citizens, so that can be the beginning of action. We had an amazing experience with Treepedia, sharing data about trees worldwide, and then citizens from cities all over the world were trying to use this data in order to ask the mayor, can you plant more trees in my neighborhood? Richard asking, how do we design to move freight? It's a good question. We didn't talk about it, not with drones. I will say we can talk about this next time. It's a long question, but I think freight moves best on the ground and with robotics. And there's a few startups working in this space. Both self-driving cars and so on. And then the last point by Sean, which is also crucial, is about the issue of disability that we didn't address. You're absolutely right. Actually, I'll tell you something we're doing with disability. We're using artificial intelligence to analyze a huge number of images, especially Google Street View images, in order to look at the level of accessibility of a city. And again, if we're able to measure that, again, that will put incredible pressure to public administrators, to mayors, in order to make certain neighborhoods or cities which are not accessible, not sufficiently accessible still to date, and to take action in order to improve them. And so I think we want to do what you can do. The beautiful thing about what you can do with AI in terms of deep learning is that it does very, very well what we can do as humans to look at something and understand, recognize, understand features of the city, classify them. And so we're trying to train AI in order to detect all of those inaccessible points in the city, so that then we can fix them. Sorry about this, but I really wanted to answer those questions. I thought, as you typed them there, and delighted to continue conversation at the time.
Thank you, Carlo. I think just for the students who are on this call, we have the Q&A session. We just have that delayed a little bit. So hopefully you'll get to, if you have time, you'll be able to talk to them as well in the Q&A session.
Oh, sorry about that. I thought we were not. Sorry about that. Okay, so then apologies then. But anyway, I anticipate some of the Q&A questions.
No, I just wanted to make sure, because so the students know that we still are planning to have the Q&A session as well with them. Okay, so can you see?
Maybe on COVID, let's go back to COVID if it's okay with you. And it's something that I learned and I realized as well, and I've been thinking about it. It's not something that I think what's going to happen next, I don't know. But aging infrastructure we designed for a very long time, I've been talking about for 100 years and that sort of thing. And we also do prediction, and that's a policy. How is this infrastructure is going to be used? And so you predict the usage of demand for long term. But then I think what we're realizing is that the demand of aging infrastructure rapidly changes, much more in decades and that sort of thing. But I think COVID really taught us, or taught me, it can change rapidly if it wants to, and if something happens, meaning that the demand can change rapidly, and therefore our infrastructure design has to cope with that kind of change as well. And that may not happen, although we think about 120 years design life, we have to think about design in much shorter time frame and see how the infrastructure is used. So that's something that I realize, and hopefully many of us realize, is that the demand can change rapidly rather than, and we all know that it changes in decades, but decades can be very long for many of us. For younger generation, decade is like a very long lifetime of them. For like me, it's quite a sort of a decade is short, but then at the same time, this change is so rapid, and that's something we need to think about. And that's a paradigm shift in terms of how we design our infrastructure. So I think that taught us. And I think that's Jeffrey was trying to say as well.
Kenichi, I think for me, the issue that has been most centered and surfaced during the pandemic has to do with issues of disparity that become legible and visible across questions of race, gender, issues of disability, age, across citizens in space. And this is the primary question for me around how we collectively within professional organizations, both in the training of our next generation and in the advocacy that we undertake for the next infrastructures that we build, can start to conceive of the aims of infrastructure as essentially being those systems and their physical materialization that enables the good life for all citizens. And if we can't think about how to address fundamental issues of inequity at the moment where we begin to think about servicing society, then we will produce more of the same, regardless of the levels of technology that we integrate into these systems. So for me, that's the most pressing issue that's really been made vivid by the pandemic.
Thank you, everyone. In the interest of time, I'm just going to go around Zoom and ask our panelists like their final thoughts on this topic before we wrap up the panel discussion.
Carlo, do you want to start first?
Oh, sure. Okay, sorry. I feel I've talked too much. So I didn't know if you wanted to go anymore. But you want us to comment again on the final topic on this topic? You mean again on the post-pandemic city, or?
No, in general, on the idea of sensible cities and making our cities sensible to accommodate a lot of the issues that we discussed related to COVID, related to disparities, disability. Like, where do you see the future going?
You need to ask me as head of the Senseable City Lab, about the making our city sensible. I'd be certainly you're preaching to the converted. I'd be certainly an advocate. But I think the point is on what are the key principles. And I think in the discussion we really touch upon quite a few of them. It's about environmental sustainability. We talked about certainly about circularity in terms of material. It's about the energy consumption and CO2 emissions. It's about air pollution, and then certainly how that intersects with the social sustainability. So, all the issue about biases, about disadvantaged community. There's a map I didn't show from our work that looks at, where you got pollution and where you got disadvantaged community, and you see this clear overlap. So somehow, how we can look at the intersection between the environmental issues and the social issues. So I think, that for me is really the urban agenda for the next few years. I wanted to add another thing. It's part of it. Some of you are interested. We're having a conversation. There's a good venue for conversations on cities is what's called the Bloomberg City Lab. And there's a big conference every year that we will happen in a few days. And as part of that, together with Saskia Sassen, and some of the students might be familiar with Saskia's work as a sociologist at Columbia, and the author of Global Cities and many other books. And so we just did an op-ed, an editorial together about one thing that's very important when we think about social sustainability in cities after the pandemic, is that we have a big risk. And the risk is if you look at the statistics today in Boston, in New York, I think probably in many other cities, but suppose in New York, you got up to 30% of businesses that shut down and are not expected to reopen after the pandemic. And we got a lot of companies downsizing their office building, their office footprint. And if you don't do anything, we might end up with zombie neighborhoods for a number of years. It might kill the very fabric of the city. So what we should do, and we are calling this the duty to the city. The duty to the city for us is the duty to make sure that every asset in the city is used, and making sure that out of the pandemic we can really quickly transform and repurpose real estate and make sure that we don't leave some neighborhoods half empty. So we propose this as a principle. Of course, the duty to the city relates to the famous right to the city, or in French, le droit à la ville, which was theorized by Lefebvre, again, a great sociologist in the second half of the 20th century. So somehow that as well, which is part of this broader notion of sustainability, is what can guide us as we move out of the pandemic.
Maybe a few words from me is that I think we all age, and the point is that our infrastructure is aging, and we suffer from aging infrastructure nowadays, and we have to cope with that. Our new technologies are coming in to cope with that particular challenge, and that's what we need to do. And I tell my students, for example, is that can we make our infrastructure doesn't not age? So if keep on young and then keeping operative and good to keep demand, sort of cater the demand. So infrastructure doesn't change, age will be one way of looking at it, or infrastructure that will elegantly age. So it may decline or it may sort of go up, but then just elegantly age, and therefore, so that really gives a demand, sort of a change in the way we design, I think, our infrastructure. And I think all the discussion we had, I think sustainability and all these things are related to that particular thought, I think. Thank you.
For me, I guess I've been thinking a lot about the UN Sustainable Development Goals as a framework which somehow is occurring in a kind of relatively recent moment. Think about what the fundamental rights for humans are. And this totally relates to Carlo's reference to Lefebvre and the right to the city as a concept. I wonder how we see the right to information. If we think about aspirations of the so-called developed world and the delivery, for example, of drinkable potable water to every point of contact for all citizens as an infrastructural effort that's been going on ultimately for millennia. If you look at the city of Rome and you look at the Roman Empire and the system of aqueducts in Italy to deliver this idea of fresh drinking water to the city as a fundamental construct of residing within the city. I wonder how we think about this issue of access to information today. And it's astonishing to me when we talk about issues of the digital divide that we are not already really centering and surfacing this question of data availability fundamentally related to information availability, as well as participation in the smart or sensible city of the future as a fundamental right that should be delivered freely to all residents of cities.